Okay, hello everybody, welcome back. This is day 10. Going to be talking about two basic rules in contingency tables. As an overview, still early in Unit 2, we already discussed basics in probability, and now we're going to talk about a few more rules. Following this, we're going to start talking about random variables, specifically discrete random variables and their parameters. And then we're going to look at two examples, which is binomial and Poisson random variables. And then we're going to talk about continuous random variables and the important theories that come after that, which is theories about the distribution of sample means and the central limit theorem. We're going to use those to identify point estimates and confidence intervals. All of this is going to prepare us for hypothesis testing, which is what we find in Unit 3. Following our discussion on point estimates and confidence intervals, we'll have our second celebration of knowledge, which will cover chapters 3 through 8. The goals for the lesson are to know and be able to use the addition rule, multiplication rule, and Bayes' theorem. Understand what a contingency table, tree diagram, and Venn diagram are and how they are used. So that's what we're going to be discussing. A Venn diagram is a picture, some visual representation, that can represent the outcomes and events of an experiment. There's a box for the sample space. It's this box right here, S, which we'll call the sample space. And events are drawn within the sample space, usually as circles or ovals, as seen here. So we've got event A, and remember, an event is a collection of outcomes. So if this experiment were rolling a six-sided die, right, A could be even numbers. And so what would be in set A? 2, 4, 6. Okay, and then B, what if B were numbers less than 4? All right, then B would contain 1, 2, and 3. Now 2 is in both of these events, so it'd be better to write 2 right there. It's in both. See, it's still in A, and it's still in the circle B. But it's in both of them, so I'm going to put it in this overlapping area here. This is called the intersection. 4 and 6 are rightly drawn in A but outside of B because they are not in B, as is 1 and 3. It is in B but not in A. And then C, and so C could be numbers that are equal to 5. And so that would be 5. 5 is not in A, nor is it in B. And so it's sort of all by itself, and there's only one outcome in that event, a very simple event. And then there is nothing in the sample space that is outside of these three events. But in general, you could have numbers that are outside of this event. Like if we were using a 10-sided die or something, a 7 and a 9 would be outside of the event A and the event B. Often in these Venn diagrams, you will see numbers written in them, but they don't represent the outcome. They represent how many outcomes are in the set. So this here, we've got one element in that set. B has 3 elements total. 2 elements are in B and not in A. 1 element is in B and A, and 2 elements are in A. And there are 0 elements outside of S. So again, we're thinking about a 6-sided die. So the experiment is a single roll of a 6-sided die. So brown is the actual outcomes and purple are the outcome counts. And so if we add up all of these outcome counts, 2 in A, not in B, 1 in A and B, 2 in B, not in A, and 1 in C, and 0 in the sample set, if we add all those, we get the total number of outcomes, which is 6. Okay, so let's use our new tool, the Venn diagram, to understand what's called the addition rule. So the Venn diagram is a depiction of the outcomes and how they intersect with other events. So if I wanted to find the probability of A or B, so this shape here in the purple, if I wanted to find that probability, well, what I can do is I can find the probability of it being an A. Okay, so all of these outcomes together with all of these outcomes, but notice I am there is an overlap right here. All of these outcomes are counted twice. If I add the probability of A and the probability of B, I'm going to get the overlap. So I need to subtract that overlap, and so that's what's going on here. Subtract A and B. So this region right here is A and B in blue. Okay, so that is the addition rule. The probability of event A or B occurring is the probability that A occurs plus the probability that B occurs minus the probability that they both occur at the same time, because that was double counted in these terms here. And then this next line here is the exact same thing, but it's just written with different notation. We use the union for or and the intersection for and. Okay, tree diagrams. Here is another tool that will help us with another rule. So tree diagrams help us visualize experiments that can be broken into stages, such as sampling. Each stage is its own level of the tree. At each stage, make a branch for each possible outcome and write the probability of the outcome on the branch. After all stages are completed, the leaves represent the final outcomes of the whole experiment. Okay, so this is best understood by an example. So let's go ahead and take a look at the example. A drawer has 7 socks, 4 are green and 3 are white. What is the outcome of 2 draws? So the experiment here, we're sampling from a drawer of socks, right? We're just picking out 2 socks, and we want to know what the total outcomes are. Now this simple example is basically the same idea as if I had a population of 1,000 SVU students and I had to select some of them, right? I had to randomly sample from that. Okay, so I've got 2 different draws. Event A is the event that the first draw is green, is a green sock, and event B is the event that the second sock is white. Okay, so let me draw out my first draw. So I have 2 options here. I could either get a green sock or a white sock. Now, the green sock has a probability of 4 out of 7, 4 sevenths. The probability of me drawing a white sock is 3 out of 7. Okay, now let's look at the second draw. Because the second draw depends somewhat on the first draw, right? Because the amount of socks in the drawer has changed. I'm going to start here at this. So if it was green and I do my second draw, my options are still getting a green sock or a white sock. But now, what's the probability of getting a green sock? See, so remember, a sock was taken from the drawer, and it was green. In this case, at this branch of the tree, we know that it was green. And so now there are only 3 green socks after one has been chosen. So this is going to be 3 out of what's the total now? The total number of socks are 6. So at this branch, it's going to be 3 over 6. And then for white socks, there are still 3 white socks, but there's really only 6 socks total. So there's that probability. If a white sock was drawn first, I still have the option of getting a green sock or a white sock. Now, if a white sock was chosen at the first stage, there are now only 2 white socks and 6 socks total. And there are 4 green socks. And so the probability of my second draw getting a green sock is going to be 4 out of 6. And the probability of getting a white sock is now going to be 2 out of 6. Okay, now each branch represents an outcome here. This first branch is going to be green, green. That's me getting 2 green socks. The next branch is me getting a green sock in the first draw and a white sock in the second. The third outcome is going to be this path right here, which is a white sock. So each path to the leaves these are the leaves. Each path to the leaves leads to a potential outcome. And then the last one is white sock, white sock. So the big question here is, what is the probability of A and B occurring? Well, A and B is this right here. This is the only outcome that's in A and B. So A and B is an event that has only one outcome in it, and that is GW. Green, first draw, white, second draw. And so the probability of that is going to be what? 1 in 4, right? Wrong. Not 1 in 4, because these things are not equally likely. In order to compute this probability, I've got to think the probability of getting the green sock first is 4 out of 7, and then after that has happened, I have a probability of 3 out of 6 of getting that white sock. And so I'm going to multiply, because these things are happening in stages. And so the total answer there is going to be 12 over 42, which simplifies to, actually, let me simplify this before I multiply. That becomes a 2. That becomes a 1 if I cancel out the 3's. And I can even cancel out, here becomes a 2. So the answer here is 2/7. So that's the probability. Notice I can follow this path, multiply the probabilities, and get the total probability for that outcome. Now I need to talk about the difference between with replacement and without replacement. This experiment here was done without replacement. I did not put the sock from the first draw back. And so these probabilities right here were different because it depended what that first draw was. So A and B are not independent if I do it without replacement. However, they are independent if I sample with replacement. Okay, now what would with replacement look like? Well, I would have my first draw, and it could either be green or white. And the probability of green is 4 over 7. Probability of white is 3 over 7. Now, my second draw, I also have those same two possibilities, but I have put whatever sock I drew, I put it back. And so in my second draw, I still have a probability of green at 4/7 and a probability of white at 3/7 because I put the sock back. And this is all the same here. Okay, so this is with replacement. This is without replacement. Okay, and so we used our tree diagram in order to figure out the probabilities of the outcomes of a two-stage experiment in which there were two trials, one draw and then a second draw. And that brings us to conditional probability, the probability of an event occurring given or conditioned on some other event occurred. And the notation is the probability of A given B. So we do this vertical line here that means given. We have seen conditional probabilities from this tree diagram. So this right here, 4/7 is the probability of A, that first draw. And then what we have here, the 3/7 is the probability of, well, not A. Probability of A complement, the opposite of A happening, which is a white sock, since there's only green and white socks. And this right here is the probability of B happening given that A has already occurred. This one here is the probability of B happening given A prime has occurred. So that's 2/6. Okay, well, hopefully this is all coming together. If it's not coming together now, hopefully the homework will do the trick, and certainly you'll have the opportunity to ask questions in class when we discuss this next time. Okay, so more on that later, because there's a Venn diagram approach that I'm going to show you, and hopefully that'll help clarify this. But for the moment, let's just ask this question here. Does P of A given B equal P of B given A? And so let's just say that A is the event of randomly choosing a person. If you randomly choose a person, what's the probability that that person will be Catholic? What's the probability that that person will be Catholic? So that would be the probability of A. And then B is randomly choosing the Pope. Well, let's do probability of B given A. Probability of B given A is what's the probability the randomly chosen person is the Pope, given that person was Catholic? Well, there's about 1.3 billion Catholics in the world, so, and there's only one Pope, so that would be something like 1 over 1.3 billion, which is effectively 0, or you might write 0 plus. It's not exactly 0, it's not equal to 0, it's 0 and a little bit more. So sometimes you'll see 0 plus. Okay, but on the other hand, what's A given B? Well, the interpretation of A given B is what's the probability that a randomly chosen person is Catholic, given that that randomly chosen person is the Pope. So we're assuming that B has occurred. We have chosen the Pope. What's the probability of them being Catholic? That is 1. So the probability of A given B and the probability of B given A are not necessarily the same. They could be almost as different as possible. One way could be 0 and the other way could be 1. Thinking that these are the same is called confusion of the inverse. You're sort of inverting the order of A and B. Okay, so the multiplication rule is nothing more than what we basically discussed in this table right here. So, see, the probability of A and B is the probability of like this first choice, the probability of A times the probability of B given A. So that's what we have right here. So we've already seen an exhibition of this rule. Probability of A times the probability of B given A. Or you could switch the order around. The probability of A given B times the probability of B. Whatever is in the bottom, that gets its own probability. All right, now what if A and B are independent? So remember in that example with the tree, if you don't mind me scrolling back up here, remember with this example in the tree, A and B were not independent. They were dependent because it was done without replacing the first sock. So they were dependent. Now what happens if they are independent? Well, the definition of independent says that the probability of B occurring does not affect the probability of A. So what that means is the probability of A given B, if they're independent, is exactly the same as the probability of A. The occurrence of B does not affect the probability of A. The probability of A and B is going to equal the probability, right? So in general, it equals the probability of A given B times the probability of B. But if they're independent, then the probability of A given B is the same thing as the probability of A. And so if they're independent, then the probability of them both occurring at the same time is just the multiplication of the two probabilities. So that's nice and easy. So we like independent events. Okay, Bayes' theorem and a little bit of a Venn diagram to help us see some things. Bayes' theorem is just a way of writing A given B, probability of A given B. So recall this multiplication rule from the previous slide. If I solve for A given B, probability of A given B, I'm going to get probability of A given B is going to equal the probability of A and B over the probability of B, right? I just divide both sides by the probability of B, right? I just divide both sides by the probability of B. And so this right here is Bayes' theorem, or Bayes' rule. And it uses the AND rule. This tells us something very interesting. So the probability of A given B has the probability of B in the denominator. Pictorially, it's this area here divided by this whole area. So you think of B as the sample space. So when you're conditioning on B, B becomes the sample space, and now the event we're interested in is just where A and B intersect. Okay, so that is yet another way of thinking about conditional probability. All right, so let's do a little intermediate recap here. We talked about 3 basic rules. We learned about Venn diagrams and then used it to talk about the addition rule. Then we learned about tree diagrams, and they facilitated our learning about the multiplication rule. We also talked about sampling with and without replacement. And then we talked about conditional probability and Bayes' theorem, which helps us to understand conditional probability better. Okay, you don't have to write all that down. I just hope it clarifies what it is we have done. Now we are going to put all of these rules in practice as we talk about yet another conceptual tool, contingency tables. So a contingency table is a two-way frequency table. It tracks the frequencies for 2 variables. This is bivariate categorical data. Okay, so that's all a contingency table is. It is a two-way frequency table. Now, how it is used, there's a lot we can say about that. Let's begin with an example. So, first, we've got this study where we're trying to study the accuracy of a drug test. And so bivariate data is taken. For each subject, they are either identified as a drug user or a non-drug user, and they are given a drug test. The N and the U, N is for non-drug user, U is for drug user, and the minus is for a negative test result, and the plus sign is for a positive test result. And we do this for just a bunch for all of our subjects. So we've got this big list of bivariate data. Each one of these represents a single subject. And then what we do is we count up according to this table. So how many people were drug users and a positive test result? So there was 43 of those. How many were non-drug users with a positive test result? 7. Negative test result was a drug user, 24, and so on. And so that's our contingency table. That's called the contingency table, a two-way frequency table. The 2 variables here are whether they're a drug user or not, and their test result. 2 variables. Okay, now, what sort of questions might you have? So these questions here. We can find out these questions. Okay, so back to our example, and I've copied the contingency table for our convenience. U is going to equal the event that we randomly select a subject, and that subject is a drug user. And then the plus sign is going to be a symbol to represent the event that we randomly select a subject that tested positive. Okay, now, what are the following probabilities, and state what they represent? So this first one here, the probability of, and then it has a big U. And so this is the probability that we select a user. Now, we need to compute this probability. And so we are going to use the empirical or relative frequency approach to doing that. There are how many users? 43 plus 24 is 67. So there's 67 total users. How many participants are there? 500. So there are 67 out of over 500. And so the probability of randomly selecting a drug user is going to be 13%. Okay. P of plus sign, in this case, is going to mean we randomly select somebody with a positive test result. And that probability is going to be, let's see, positive test result. There's a total of 50 of those. And I'll bet this one here is 450. Yeah, 450. So the probability of getting a positive test result is going to be 50 over 500, which is just going to equal 1/10. Or 0.1010%. Okay, now what's the probability of getting, of U and plus sign? And so that is going to equal the probability of selecting a participant who is both a user and has a positive test result. All right, and so this is going to be P and plus. So that is and. So that is going to be this one, this right here. That is the number of people who are a positive test result and a user. So that is going to equal 43 over the total 500, which equals 0.086. So about 9%. Okay, now these conditional probabilities. What is the probability that someone is a user given a positive test result? Now that is a very interesting question, right? What's the probability of that somebody is actually a user given a positive test result? We'd like the answer to be 1, right? To be 100%. That would be true if this test were 100% accurate. But let's see what it actually is. Okay, but let me write down the interpretation first. It's going to be probability. So the probability of randomly selecting somebody who has a positive test result and is a user. Okay, now this is going to equal, and we're going to use Bayes' rule. Bayes' rule says that's going to be P of U and plus sign divided by P of plus sign. That's going to equal 43 over 500 divided by plus the probability of getting a plus sign, 50 over 500. Notice that the over 500s cancel. If I multiply top and bottom by 500, those would cancel out, and I would just get 40 over 50. And notice again that this is sort of like that Venn diagram. The positive test result here has become our sample space. That has become our sample space. And so now it's just how many users in that sample space, there's 43, out of the total, which is 50. So two different ways of computing that. And that becomes 86%. So there's an 86% chance that somebody who got a positive test result is actually a user. It's pretty good, but I don't know. I'd like it to be better. Okay, and now for the last one. And that's the probability of a randomly selected user, we're assuming that they're a user, getting a positive test result. Okay, and that again is going to be P of U and plus sign, which is the same thing as plus sign and U, divided by probability of user. And that is going to equal 43 over 67, which equals 64%. 64%. So there's only 64% that a user will get caught, according to this data. Okay, before we move on, let's draw a Venn diagram. Okay, so this is going to be the total, the sample space, or the total set of participants. This one here is going to be U. This one here is going to be plus sign. There's going to be 43 people in here. Users that did not get a positive test result is 24. People that got a positive test result but was not a user is 7. And then everybody else, that would be people who are in neither of these. That's going to be 426. And if I add these all together, I get 500. Great. And so I could have used this to find my probabilities. Cumbersome calculation guideline. The cumbersome calculation guideline says if you are sampling 5% or fewer of the population without replacement, and remember, without replacement means it's dependent, you can do the math as though it was with replacement, as though it was independent. There are so many in the population that the calculation is hardly different from if you just assumed that these were independent, that you were replacing. I.e., if you are sampling less than 5% of the population, the draws can be regarded as independent. Remember, we like independent draws because you just multiply the probability at each time. So there's the cumbersome calculation guideline. We will talk more about that, and hopefully that'll help it sink in. Okay, the complement rule. So back to the complement rule, and here's an example of that. And this is the at least one at least one usage. So what is the probability of randomly selecting 10 subjects from our drug test study and getting, all tested positive? So probability, all 10 tested positive. So we are sampling 10 people, and we want to know the probability that all of them are positive. And so what that is that's something like this. Probability of first draw positive, and all of them need to be positive. Second draw positive, and third draw positive, ... all the way to 10th draw positive. So that's big probability, and, all these ands, 9 ands. Now this would be very difficult to compute. However, because we are only sampling 10 from 500, 5% of 500 is 25 people. 10 is less than 25 people, 5%. So, cumbersome calculation guideline, which I'm going to evaluate, is CCG. Because of the CCG, the 5% CCG, cumbersome calculation guideline, we can regard these as independent draws. Wonderful. And so that's going to equal the probability of plus sign, of getting, of the first one being positive, times the probability of the second one being positive, simply times the probability of the third one being positive, all the way to the probability of the 10th one being positive. We are using the cumbersome calculation guideline to say that all of these are effectively independent. And so what that gives me is 10 copies of p times p. So that's where I use my exponent. P to the 10th times p to the p plus to the 10th. And what is p plus? Well, that's up here. 0.1. 0.1 to the 10th, which equals 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there it is. Very, very, very small number. That's the probability of randomly selecting 10 people and all of them tested positive. And that should be rare. That should be very small. Now let's do this other one, which is the probability of at least one. At least one of the 10 is a user. So if A is at least one of 10 are users, the opposite of that, A complement, is none are users. Now, none are users is a bunch of ands. First draw, not a user. And second draw, not a user. And third draw, not a user. And there's a lot of ands there. So the probability of this is going to be probability of U complement times probability of U complement. Again, because we're sampling less than 5%, we can just multiply all of these. Probability of U complement. Probability of U complement, as our rule just below us indicates, is going to be 1 minus probability of U, and we raise that to the 10th. And so that's going to equal, what's the probability of U? So where was it? The probability of U is 0.134. 1 minus 0.134 to the 10th. That's the same thing as 0.866 to the 10th, which equals 0.237. So that's the probability of P of A prime, right? All or none. Now what I need to do is if I want to find the probability of A, I need to take 1 minus the probability of A prime. And that gives me 1 minus 0.237, which equals 0.763. So 0.763, that's the probability of getting at least one drug user out of a draw of 10. And so that's good. It shouldn't be too improbable. Okay, summary of rules. From last time, we have the complement rule. P prime, remember that was a way of saying the complement, is going to be 1, which is everything, the probability of the sample space, 1 minus the probability of the event occurring. The addition rule, the probability of A or B, A union B, is the probability of A plus the probability of B minus the intersection, the probability of A and B. The multiplication rule was the probability of A and B is, and this is always going to be true, the probability of A given B times the probability of B, or the probability of B given A times the probability of A. Now, remember, if they were independent, though, then we can just multiply like this. But if they're not independent, the multiplication rule always holds. Okay, Bayes' theorem was this right here, just a nice way to help us understand conditional probability. If the events A and B were mutually exclusive, then the probability of the intersection is 0. And that makes sense from our Venn diagram, right? If they were mutually exclusive, then there is no intersection. So the intersection is just 0. There's no outcome common to both of those events. Both of the events cannot occur at the same time. No common outcome. All right, and remember, if they're independent, then the probability of B does not affect the probability of A, and so the probability of A assuming B is no different from the probability of just A. Okay, and now we have our Boromir meme. Is it true? Do you simply add probabilities if they're mutually exclusive? So the probability of A union B by the addition rule, but if they're mutually exclusive, this is going to be 0. And just as Boromir says, one simply can just add probabilities if the events are mutually exclusive. Okay, recap. We talked about a whole lot today. First thing we talked about was Venn diagrams, which is a very useful conceptual tool. It helped us to understand the addition rule better. That brings us to the addition rule. After that, we talked about tree diagrams, which is useful in understanding multi-stage experiments. And that introduced the multiplication rule. And that brought us to conditional probability. After that, we looked at Bayes' theorem, and then we started talking about contingency tables. And we used all of these ideas. We used the conditional probability, we used the multiplication rule, and we used, and we saw how you could write the contingency table as a Venn diagram. We then talked about the 5% cumbersome calculation guideline, and saw how it was employed as we did an example in which we sampled 10 people from our drug test study. And then the last thing we looked at was a little example in which we looked at the probability at least 1. Okay, and that was it. All right, everybody. Sorry that was so long today. Please come to class and ask questions about any questions you may have. And we'll see you next time. Thanks.